Now that we've considered the forward dynamic analysis and the inverse dynamic analysis separately, we can actually now go and combine the two as well. And that BC, the workbench, is able to handle that as well. We'll see in a moment that what will actually happen is that when we specify some sort of a rotation driver, that the system will actually apply a braking torque when it calculates the Lagrange multipliers. Now, to perhaps illustrate why I used the 6 Newton meters in the calculations and the formulations that we did in the spreadsheet, or the mind map rather, what I'm first going to do is just run this pendulum rod E in the case that we didn't have a forward dynamic analysis problem. So I'm just going to comment out the actual torque that I specified over here and just remove it from my forces list as well. And then I can also just go and check that I still have the function available over here. So I'm just specifying a relative rotation driver for my system. I have the equation over here, so this is just the coefficients that I specify for the type A function. So this is the same that we had for lecture 3. So in essence, what I'm doing over here is just rerunning the actual inverse dynamic problem. And what I'm going to do is I'm just going to type in over here DAP, then it asks which folder contains the model. So I'm just going to say PR_E, and then it asks whether I want to correct the initial conditions. As usual, I want to correct it since it's good practice to just make sure there's continuity in the system. And I can also then double check that my corrected coordinates do indeed correlate with what I gave in as input. So we do have the correct XY coordinates, and we know that the system also starts at minus 30 degrees. Then it asks for the final time. So in my case, I'm just going to say, let's perhaps do 30 seconds. And then we can use a reporting time step of, let's maybe make 0.1. Okay, and we see it terminated after about 1,200 iterations or function evaluations. So once that is done, I can then go to post. And then I'm just going to look over here in my workspace for the variable lam. So this is where the Lagrange multipliers are specified. And if I open up this one, we'll see that the form is a 301 by 3 matrix that I have over here. So the 301, of course, corresponds to the number of time steps that I have. And then the 3 corresponds to all of the Lagrange multipliers or the reaction forces or moments that I have on the system. So you will remember that for our original case where we didn't have any constraint specified, we just had a revolute joint, that was then specified as joint 1. And that specific type of joint induces 2 reaction forces, one in the x direction and one in the y direction. In this case, J1 is still that revolute joint. If I go back to J in joints over here, you'll see that J1 is the revolute joint. So in the actual Lagrange multiplier field that I have over here, Lagrange multipliers in column 1 and 2 will be the respective x and y reaction forces that I'm going to consider. However, the one that I'm more interested in is then Lagrange multiplier 3, and this is the one that refers to the torque that is then being applied on the system. Since I have a relative rotation driver, I specify the motion and then I measure the Lagrange multiplier as the torque that I'm getting as output. And if I'm perhaps interested in what the maximum value is, we can see that it's about 5.9, but I can also go and just say max LAM. I'm going to test it over all the time points just for Lagrange multiplier 3. And I can see the value is about 5.9111 that I get over there. So that's then in Newton meters. Since it's a positive value, it means that it's in the counterclockwise direction. So by specifying the relative rotation driver, which induces a 2 pi over 60 radians per second square acceleration, the resulting Lagrange multiplier, which is then the torque, is going to be 5.9111 counterclockwise in Newton meters. So now that I have this, what I can actually go and do is then specify a torque as well. So now I'm going to combine the inverse dynamic analysis problem with the forward dynamic analysis problem. And since this value of 5.9 is sufficiently close to 6, I'm just going to round up to 6. And we then did that under the inforces file over here. So I'm just going to uncomment S2. And I'm just going to make sure to add it over here as well. So I'm just going to say S2. So now we have both under in joints we have a relative rotation driver, so that's an inverse dynamic analysis. And then I also specify an applied torque of 6 Newton meters, and that corresponds to a forward dynamic analysis. So this is now a combined dynamic analysis problem that I'm considering. If I now go back, I can just say clear all, close all, just to make sure that I'm working with a blank workspace. And then I'm going to type in DAP. The model is once again PR_E. I once again want to correct the initial conditions. I can see that my X and Y coordinates are still correct, and the initial degrees is also -30, so that's also correct. And now the final time, I'm once again going to use, let's say, 30 seconds over there, and then my reporting time step will still be 0.1 seconds. And once again, we can see it terminated after 1,200 function evaluations. So now what I can go and do is I can run the post, and this post processor will then generate the new Lagrange multiplier values over here. And if I now look at these values, what we actually have is now negative values for the torque relating to the relative rotation driver. So what this basically tells us is that although I'm specifying that 6 Newton meter torque, what the relative rotation driver will actually do is apply a braking torque once I reach that 2 pi over 60 radians per second square acceleration that I specify. And that will ensure that across the entire 30 seconds that this thing runs, that the rotational acceleration will remain constant in accordance with the actual relative rotation driver function. And to perhaps illustrate this a bit better, we can rerun the post plotter. So if I go over here, we can see that I have figure 1, which is just the coordinates of the points. Figure 2 is then those coordinates with respect to time. And then I also have the Lagrange multipliers for the reaction forces at the revolute joint. Figure 4 will then be the accelerations with respect to time, so the linear accelerations in the X and Y direction. Figure 5 is then the actual angle that I'm testing as well. And then over here I have figure 6, which we can now consider. So I'm just going to uncomment that by pressing Ctrl, Shift, and R. And then figure 7 over here is the rotation acceleration that I want to check for the pendulum rod as well. Okay, so I'm just going to run the post plot script, so I can just press over here on this gear button. And then perhaps starting at figure 1, which is then the coordinates in the X and Y directions, we can see that this is more or less as expected. As we saw, the initial angle is -30 degrees for our pendulum rod, so we expect, since it starts from 0 velocity, that the points will be a bit closer to one another, and as the system then accelerates, the distance between the points grows larger, and this is indeed what we see over here on this graph. Then for figure 2 as well, these are just the X and Y coordinates with respect to time. And since we have acceleration, we expect this oscillatory motion to cause the frequency to increase, and thus the period of these oscillations to decrease. That gives us an indicator that we are actually working with an accelerative system. Then for figure 3, these are just the reaction forces in the X and Y directions. And we can see that's -20, 0, and 20 that we start off with, and then we have some oscillations later on once we've reached higher velocities over here. Once again, we can also go and define the actual velocities, or I think figure 4 is actually the accelerations with respect to time that we're looking at. So the accelerations in this case we can actually see are increasing, and at the end we have this 3 meter per second square magnitude for the acceleration. The X and Y components oscillate, so that is also as expected. We don't expect to see a constant value for our linear accelerations, but we do expect to see a constant value for our rotational acceleration, since that is the type of driver that we're specifying. In this case, we also have 3 meters per second square, so this is much smaller than the original 750 meter per second square that we had if we just specify an applied torque. So if we just specify a forward dynamic analysis. So this already tells us that there's some sort of a braking torque that is being applied to minimize this acceleration over here at the end, or to at least ensure that the acceleration is as what we had for the inverse dynamic problem. Then if we look at figure 5, this is simply the rotation angle. We can see that it starts over here just below 0, so this is minus pi over 6 if you go and check this value at the bottom, and it then goes up to about 46.51 degrees. Then if we look at the comparison of the torques over here, then you'll see that we have an applied torque. So the applied torque we know is 6 Newton meters, and this is applied throughout the entire time interval 0 to 30 seconds. Then we have the inverse dynamic analysis torque, and this one I got directly from the relative rotation driver function. So if I go back, you'll see over here we have lam, which is then the Lagrange multiplier. So I basically just extracted those values, and these correspond then to what we expect for an inverse dynamic analysis problem. So I've just plotted those as well, and then our resultant torque will simply be our applied torque plus this IDA, or inverse dynamic analysis torque. And then we get this blue line over here, and we can see that it oscillates between 6 and minus 6 Newton meters. Okay, so then we can also lastly look at the rotational acceleration, and in this case what we have is a constant line. This is indeed what we expect over here. The reason being, we specify a relative rotation driver. We know what the rotational acceleration is. We know it's a constant. If we integrate it twice, we get the driver function that we specified, and we specified it initially, the rotational acceleration, as 2 pi over 60 radians per second square. Over here I can see the value is about 0.104 or 105. So if I perhaps just want to go and double check that, I can say 2 times pi over 60, and I indeed get about 0.105 radians per second squared. So this gives us confidence that the relative rotation driver actually applies a braking torque to prevent the rotational acceleration from changing from the prescribed 2 pi over 60 radians per second square. So if we, for example, didn't have the relative rotation driver, so if we look at PR underscore D again, you'll remember that over here we had a force that we specified, so just the applied torque, but our function, we didn't have any function over here, so we didn't apply any relative rotation driver. So if I'm interested in how this function's acceleration will look, what I can maybe first do is then run DAP. Then I'm just going to run PR underscore D. I correct the initial conditions again, and then the final time I can actually go and make it a bit smaller this time. So let's make it 3 seconds, and then I'm going to use 0.01 seconds as my reporting time step. If I then run this one, then it terminates after 1350 function evaluation, so it took a bit longer. Then I can just go and run post again. And then since I don't have a third Lagrange multiplier, if I actually check the Lagrange multiplier, I now have 301 by 2. So in this case, since I didn't specify the driver constraint, I don't have that constraint column over there, or that Lagrange multiplier column. I only have the 2 reaction forces at the revolute joint. Okay, so in other words, I'm just going to focus on the actual torque, or the rotational acceleration. So I now apply a forward dynamics problem. I want to check what the motion is going to be, and how this differs from the case where I have both a torque applied and a relative rotation driver. So once this is done, I'm just going to post plot, and I'm just going to suppress figure 6 since I don't have Lagrange multiplier 3. And then I can run post plot again. Okay, so the other properties remain more or less the same. The curvature looks more or less the same. So we can see for the angle, we once again start at minus 30 degrees or minus pi over 6 on this graph. And we go up to just above 50 radians over here. Then for our accelerations, we also have this curvature over here, and we can now see that the acceleration where we previously had about 3 meters per second square after 30 seconds, in this case we actually have only after 3 seconds we already have a rotational or a linear acceleration of 750 meters per second square. So there is no braking torque being applied over here since we don't have any acceleration limit specified. Then you can also go and check the figure 3, which is then just the reaction forces. And once again, these reaction forces are much larger. Previously, we saw with the braking torque or the relative rotation driver specified, the force was around 20 Newton. In this case, our force after 3 seconds is already at 1,520 Newton. And then you can also just go and check the actual coordinates of the center of mass of the pendulum rod, and over here we can see that the frequency increases at a much more rapid rate than what we had in the case where there was a relative rotation driver specified. And lastly, we also just have the coordinates, the x and y coordinates plotted against each other for the center of mass, and we can see once again we have a few points that are fairly close to one another during the acceleration, and then or during the ramp up from 0 meters per second velocity. And then as I continue, the distance between the points actually gets larger, which is as expected. However, the important one is then for the rotational acceleration of the pendulum rod. So previously, we saw that since we specified a rotational driver, the value was constant at 2 pi over 60 radians per second squared. So something happened to actually ensure that we have a uniform or a constant rotational acceleration for the entire duration of the motion. In this case, we don't have anything to counteract this torque that I'm applying. So since it's a constant torque that's being applied, the acceleration will actually continue to basically fluctuate or oscillate between two extremes over here. So we have at the bottom about 0.66, and then at the top the maximum rotational acceleration is about 50 radians per second squared. Right, so this then also causes that ramp up that we saw with the linear accelerations. And if I now compare the two figures next to one another, so I'm first going to look at the rotational acceleration with a driver motor and an applied torque, and then next to it I can also just plot this one over here, and we can now easily see what the effect of that rotation driver was. So this sort of shows us the powerful performance that something like the DAP-BC workbench can work with. So it shows that we don't just have to consider a forward dynamic analysis problem or an inverse dynamic analysis problem. We can also consider a combination of the two, and in that case we might have some braking reaction forces or moments that are then being applied to the system. Okay, so that then wraps up what we wanted to look at for these graphs, or the different types of dynamic analysis that we can perform in the DAP-BC workbench. The last thing that I perhaps just want to show is if we look at PR_D. So in the case where we simply had a forward dynamic analysis problem, an applied torque of 6 Newton meters. Now if I perhaps go and close this and I just run this problem again, so I'm just going to say, let's just first do clear all, close all. If I now run DAP and I say PR_D, yes, I want to correct the initial conditions. I want to plot it over 3 seconds with a 0.01 second time step. So this is exactly how we ran it previously. Now if I go and I run post, and I want to plot, let's say, the coordinates of the points. So I'm going to post plot over here. So the coordinates of the center of mass of pendulum rod body 1. And let's say I actually want to use, instead of using these dots, I'm just going to use a line. And if I now run it, and we then go back to figure 1, what you will actually see is these lines that lie on top of one another. So we can see there is some difference over here uh, between the trace of the actual circle that the pendulum rod is following. So the reason for this is simply due to the actual reporting time step that you're using. If something like this is bothering you or giving you not accurate results that you want, then you will probably have to decrease the reporting time step. So this will, of course, cause the system to run a bit longer, but you will get better results over here. So once, instead of perhaps making it 0.01 seconds, I can make it something like 0.0001 second. And that will then give me a bit of a better interpolation between 2 points that are then being, that are then on the acceleration or on the actual circumference of this circle that the pendulum rod is following. Okay, and we can actually see this in the data as well. So if I go to, let's say, the accelerations, or I think this is just the coordinates of the points with respect to time, we see initially, since we still have a ramp up of the velocity, we see this smooth curvature. So it's fine for the initial motion of this pendulum rod. However, as soon as the acceleration takes over and the acceleration causes a more rapid response for the pendulum rod's coordinates, we can actually see, if we zoom in over here, we can see these spikes in the data. So if this is something that bothers you, you can once again go and change the reporting time step to something smaller. However, there is also a fine line between going too fine with your reporting time step. So in other words, the accuracy and then the computational efficiency as well. Of course, you can go as small as you possibly want to, but if it's not going to contribute to the actual accuracy or the computational performance of your dynamic analysis that you're trying to do, then it won't be necessary to further refine your reporting time step. So to strike a good balance between computational efficiency and and accuracy is paramount to these type of problems as well. Another condition that we can perhaps look at is, instead of now specifying the inverse dynamic problem where we measured the actual torque as output, we can go and check if we do a forward dynamic analysis problem and we now specify an inverse, a torque that is less than 6 Newton meters. So for that, I'm just going to reconsider, I think it was PR_D that we looked at over here. And we recall from the inverse dynamic analysis problem that the calculated torque that we need for a 2 pi over 60 radians per second square rotational acceleration was around 5.9. So now I'm just going to actually make it smaller than that 5.9. So let's perhaps try something like 4.0. And I just want to double check as well that I don't have any function specified over here. Then what I can do is run dap PR_D, correcting the initial conditions, and let's perhaps use a final time of 30 seconds with a 0.1 second time step. Okay, so this one took a bit too many function evaluations, so I think we should maybe make the time step a bit smaller. So what I'm going to do is just clear it again, and let me use dap PR_D, yes, 3 seconds with a 0.01 second time step. Okay, so now it only took 400 function evaluations. If I now go and animate what's actually going to happen to this pendulum rod, if I then press any key over here, then what you'll see is the torque that I specified is in fact not enough to overcome the acceleration due to weight. So in this case, you can actually see it's now moving down again, so it's moving in the opposite direction to the torque that I'm specifying. At this point, we can see it's now reaching zero velocity. Then the torque picks it up a bit, and then it's probably going to fall again. So we're going to have this sort of oscillatory motion over here the entire time due to the torque not being sufficient for rotational acceleration in the counterclockwise direction. Okay, so there we can once again see that's the maximum height that it's going to reach, and then weight is going to counteract that torque again, and it's going to dominate the actual motion of the system. So the inverse dynamic analysis problem that we did actually gave us information about how we can perform a forward dynamic analysis problem as well. If we are interested in having this system move in the counterclockwise direction, then we need to specify a torque that is larger than 5.9 or perhaps 6 Newton meters. Okay, so we're just going to wait for this one to finish. So of course, another condition that I can remove is perhaps the effect of weight. And I expect that if I remove the weight, then this system is actually going to move in the counterclockwise direction. Then we don't have any acceleration or any force that is going to counteract the motion or the torque that I specify on the system. But it's good practice to always include weight. It's fairly easy to do that in DAP-BC as well. So we simply specify the force as a weight acting on the bodies. Okay, so I think that's more or less the conditions that we wanted to test, the case studies, and to actually see what the results at the end of the day is. And this more or less wraps up our pendulum rod discussion as well. We did do now a forward dynamic analysis, an inverse dynamic analysis, and then a combined analysis as well on the pendulum rod. All of these were done in light of the body coordinate formulation in Prof. Nick Ravesh's PMD textbook. We simply translated that over to his DAP-BC workbench, which makes it a bit easier to visualize and interpret the results. So with that being done, the next lecture that we're then going to kick off with is the application examples. Over there, we're going to consider some more complex multi-body systems. So in this case, we only had a single pendulum body that we considered. In actual fact, we want to use this type of workbench to actually test multi-body mechanisms, where it's going to be more difficult to predict the actual motion of the system. Over there, we're also going to consider some spring mass damper systems. I know one of the application examples would also be a quarter car model that we're going to look at, and where we want to determine the specific velocities of points on the body. And we can easily do that using the DAP-BC post-processor as well. But for now, this is all that we wanted to look at. So thank you, and see you in the next lecture.